right. Well, thank you so much for joining us today. My name is Paige Valderrama Graff, and I am facilitating today's Science and Careers at NASA webinar. Joining me today is Suzanne Foxworth. She's in another room in our building, and she's going to be facilitating one of our speakers in a few moments. We are broadcasting from the NASA Johnson Space Center in Houston, Texas. This is a NASA center. We're part of the Astromaterials Research and Exploration Science, or ARES division, at the NASA Johnson Space Center, and we are so thrilled to have you all on the line with us today for our December 2016 webinar. But we're even more excited to be able to have 3 speakers to be able to share their journey to their STEM career, as well as share the work that they do with you all today. A couple of things as we get started here. First of all, our 3 speakers are Amy Jagge, and Amy is in the red shirt shown on the screen here. We also have Andrea Mosie, who you can see in the picture here on the right, and our 3rd speaker is Joanna Clark. Now, each of these speakers is going to speak for 12 to 15 minutes or so, in which they're going to aim to share their STEM career journey as well as the work that they're involved in. After each speaker's talk, we're going to give you about 3 to 5 minutes to ask some preliminary questions. Now, how many questions and answers will we get through in that 3 to 5 minute period? I don't know. We'll try to do our best as possible, but we'll keep track of all the questions that you might be asking at that time so that we can get them answered at a later time. Now, all communication will take place in our chat window. Many of you have been using the chat window already. You can see it. You can hopefully type into it. But the chat window has 3 main purposes. The first is to answer questions posed by a scientist during their presentation. Now, I know Amy's going to ask at least 1 question. Joanna will ask at least 1 question. But we don't want to take up too much of that time, so that's why there'll at least be 1 question in each of those presentations. Secondly, the chat window can be used to ask questions again at the end of each speaker's presentation. We ask that you don't type in too many questions during the presentation, because that will just be a little distracting for our guest speakers. And we will stay on the line for an extra 15 to 20 minutes after the top of the hour so that you can ask additional questions at the end of the session. Hopefully that makes sense. First of all, I want to welcome each and every one of you that are with us today. And without further ado, let's get started with our Science and Careers at NASA by turning things over to our first guest speaker for today, Amy Jagge. So Amy, I'm going to turn things over to you, and thanks for joining us, Amy.
Awesome. Okay, hi, my name is Amy Jagge, and I am a geographer and an earth scientist, image data scientist, and a GIS specialist here at the Johnson Space Center. It's a lot of titles. So I guess we'll start off with my journey. I was born in San Antonio, Texas, and when I was 12, I moved to Waterbury, Vermont. I went to high school and middle school there. After high school, I didn't go to college immediately. I took some time off and traveled. It was a really great experience for me to learn about other cultures and you know, how to live an adventurous life by, you know, maintaining my responsibilities as well. In 2010, I moved to Austin, Texas, and that's when I wanted to continue my education. Some hobbies I like to do, I like to kayak and bike ride and hike. I love to read and cook, so, you know, just a little bit about me. I furthered my education at the Austin Community College. I went there for 2 years, and I wasn't really sure what I wanted to pursue a career in, but I knew I wanted to go to school and to go to college, so I, you know, took my basic requirements and my basic classes there. And then in 2012, I transferred to Texas State University. I originally wanted to major in anthropology. Anthropology is the study of human evolution and our physical and cultural development. But when I was a sophomore, I decided that I absolutely love the environment. And I started taking water resources classes and more environmental science. And when I was a junior, I met a professor named Dr. Jensen, and she showed me a science called remote sensing, and I fell in love with it. And ever since then, I have been in, remote sensing and GIS. So that's kind of how I got to where I am today. I definitely am thankful to my mentors that have helped me open up opportunities and really, help me realize what my passions were. So, I do have a quick question. So we'll be talking about astronaut photography, and I want to kind of throw it out there to y'all. Like, why do you think it's important for astronauts to take pictures of the Earth?
So here's one of those times where we want you to put your answers in the chat window. Why is it important for astronauts to take pictures of Earth? Let us know what you think, and we'll read some of your answers as they start to come in. So Duxbury is saying to show change over time might be one good reason to take pictures of Earth from space. Any other answers out there? Leon Springs is saying it's important to observe weather, to look at what's going on Earth. Oak Forest is saying to help scientists see how Earth has changed over time. From Vintage Magnet, also to see how Earth changes. Lynn Haven from Florida. Let's see if I can, I'm losing my chat window here. Some great answers coming in, and I can't see them all, but Lathrop is saying observe weather, and Lathrop is our group from Alaska. Lynn Haven is saying to see if there's any hurricanes and be able to study it. Chester High School is saying to look at what's going on Earth. Caruthers Elementary is saying to make comparisons over time, and even to see changes in weather patterns, to see what it looks like, to compare it over time. A lot of similar answers, Amy. What do you think?
So those are all excellent answers, and actually you touched on a lot of points that I wanted to make. So first, before I talk about your answers, which are all great, I want to give you an idea of how astronaut photography works. So astronauts on the International Space Station will take images of the Earth using handheld digital cameras. So the camera to the top left is a Nikon D4, and that's one of the choices they have. And then they also get to choose from different lens sizes. So what they use on the left bottom is an 800 millimeter lens, and that will give them really close-up images with high detail resolution. And then to the right is Samantha Cristoforetti, who is an astronaut with the European Space Agency, and she is actually in the cupola on the ISS taking imagery. So to talk about some of your responses, one of the most amazing things about taking imagery from space is, yes, to monitor change over time, to measure and monitor hurricanes and weather patterns. And then also, astronaut photography provides us an aerial view, so features on the ground can be missed when you're exploring from the surface. So having an aerial view allows you to see those features so that they're not missed. And then also, like I said, you can, or like y'all said, you can monitor and measure change. So the first image we have is of the Betsiboka Delta in Madagascar, and this is a great visualization of soil erosion. So, and here we can look at how soil erosion from, upstream or in the watershed that's being deposited into the delta, how that is affecting the delta over time, and how that's affecting, populations that rely on that delta for navigable waters and trade. So that's one reason. And then here we have an image of Chicago at night. And here scientists can look at light pollution, and they can also look at population density and distribution patterns. Here is Brazil. This is, something that I love. One of my disciplines is looking at land use and land cover, and then that change over time. So here the land is being primarily used for agriculture. and it's really interesting to see how that land use has changed over time and how that use is affecting environmental conditions. And then also, one more thing that, or another thing that Astronaut Photography does in the ISS is it provides us a data set that contributes to the International Disaster Charter. And the IDC involves national and international agencies, and and they create a data set that can be delivered to emergency response, emergency management, and disaster response teams to help, populations that are being affected by man-made or, natural disasters. So this picture is of Alberta, Canada, and here you can see the wildfires and the smoke plumes. So that's a great visualization there. And then also, here is Typhoon Chaba. So astronauts can monitor and measure hurricane intensity and growth from space. So this is just an image that shows that. So talking about data from space and from the ISS, it also goes into, remote sensing and something that I do. So as an earth scientist, a lot of the data I get comes from remote sensing, and that is using electromagnetic radiation emitted from the sun that's reflected back to space and then reported onto a satellite sensor orbiting the Earth. That imagery, here's an example of a remotely sensed image. So this is Aster. It's a Japanese satellite. So we can see visible light, visible wavelengths, but there are a lot of information in different light forms that we can't see, like near-infrared and shortwave infrared. So if we use software programs and assign a color to the wavelengths we can't see, we can extract, data about it. So all the red here is of the near-infrared wavelengths, and it symbolizes healthy vegetation, because healthy vegetation will reflect near-infrared energy. So using data, I can also take remotely sensed data and put it into a platform called Geographic Information Systems, and the science of that is Geographic Information Science. And it takes layers of data and it integrates them together to tell a story or subtract or extract information. So the layers over here, this would be the remotely sensed imagery. And then you can take that imagery and create a pretty basic, easy comprehensible map. And that would be over here. Here you can see there's different ecoregions of Texas, and the legend shows you what which ecoregion corresponds to what color and what those names are. You can also make your maps a little more complicated, and be more robust and include a lot of data and a lot of information, and can be, used to deliver data or a data product to a specific scientist or someone to help someone's research. So here's a great example of GIS and remote sensing combined. Maps can be dynamic and interactive, so that you can do that by using a web-based platform. So this image right here is a base map that was provided by the software, Esri software. This is an astronaut photograph, and then this is satellite imagery. So this just shows how GIS and remote sensing can be integrated, but this time on the web instead of, a 2D map or a static map. And one other project they work on is NEMO. This is NASA's Extreme Environment Mission Operations. So NEMO is where crew members, including astronauts, will live and work in Aquarius, which is an underwater habitable research facility. So the mission will take place in an extreme environment so that scientists and engineers will have an opportunity to test procedures and tools and technology that will allow us to better prepare for future space exploration. So my role in this was to create an image acquired from underwater photography of the Carpenter Basin, which is the area that the Aquanauts will do research outside of the habitat, and create a image of the whole entire basin so that so that can be used during mission and science planning. I might have zoomed through that. but do you have any questions?
All right, so with that, first of all, thank you, Amy, for sharing this wide range of things that you do. And we're going to take 3 to 5 minutes for you to see if you have any questions you want to ask Amy in the chat window. She talked about astronaut photography, GIS, remote sensing, and NEMO. So 4 diverse things that Amy works on as she's here at the NASA Johnson Space Center and the Ares Division. So any questions that you have about Amy or about the work that she does, put them in the chat window and stand by to see if you have anything before we move on to our next speaker. So Duxbury Senior Center is asking, is that Aquanaut mission in preparation for a Mars mission? So Amy, that's a good question. What do you think?
So yes, I would say it is. It's for, you know, future space exploration in general, but yes, since I think Mars is the next journey for NASA, then it is to prepare us for our Mars mission so that we understand our, you know, the difficulties we might experience here in extreme environments so that we are well prepared when we go to Mars. And also, you know, how to meet science objectives, how to meet mission objectives while maintaining the safety of our crew, which is very important.
And some of the things that they test as well is sort of that delay. If you think about going to Mars, there could be a 10 to 20-minute delay. So is that also tested during these missions?
Yes, so they'll test about like a 15-minute communication delay. So, you know, when you make a decision, when mission operations will make a decision, you know, the astronauts won't receive that for another 15 minutes and so forth. So they'll test that delay, how to best accommodate for that. They'll also test different geologic tools so that what's the best way to collect samples and to minimize contamination.
And that's a big part of our curation, and you'll hear about curation in just a couple of minutes. Now, here's a question from one of our Arizona groups, Anasazi Elementary. They're asking, from 1 to 10, how hard is your job, and what do you like most about your job?
So I would say my job is pretty hard. You know, it's hard to give it a number or a value, but I guess I would say about a 7. You know, I feel like the university prepared me, but every day I'm learning something new. So, you know, every day I'm continuing to educate myself on new aspects of my field, and I'm educating myself on I'm constantly continuing my own research. So, you know, you're continuously learning, and that's, I think, something to keep in mind if you go into science.
So 7 is a level of difficulty, but how about on a level of enjoyment?
Oh,
how much do you enjoy your job on a scale of 1 to 10?
Like 10. Absolutely love it. Love coming to work. Love who I work with and love what I get to do. So I basically get to do what I love every single day.
And,
awesome.
And for you students out there, as you think about a career, it's that kind of passion and enjoyment that is so important. If you can love what you do, then going to work is not like work. It's like doing something you wish you could do on a daily basis. Well, that's basically kind of it. Now, one of the schools, Lynn Haven, asked about a website for imagery, and I did put that Gateway to Astronaut Photography website, eol.jse.nasa. Oops, I'll spell it right. I'll re-put that in there, nasa.gov. So we've answered that question. Here's another one for you from Oak. Let's see, Oak Forest is asking about the imagery. Here's a question from Lynn Haven in Florida. Is there a certain schedule you use to take pictures? Or that the astronauts, yes.
Yes, okay, so we, every month there is an operator, and that mission operator will create a target list. So we have different targets that are requested. We have from you know, principal investigators around the world. So they'll either be education targets or science targets. And we have a software program that we look at cloud cover, we look at solar illumination, and we decide if it's feasible to acquire this target for this day. So every day we'll create the target list, we'll send it up for the tomorrow's acquisition process, and then the astronauts will be able to refer to that target list. And we send them maps and diagrams and, you know, easily identifiable features and how to basically how to guide them to find you know, sometimes really difficult targets to spot when you're, you know, on the International Space Station.
That's awesome. And that's an everyday occurrence. So on an everyday, daily basis, this group that Amy is a part of communicates with the astronauts on the International Space Station. Now, I'm so sorry to say that we have so many questions that have come in, but not enough time to answer them all. So towards the end, we're going to come back to Amy, because I want to make sure with 3 speakers, we want to make sure that you can hear from and see each of the speakers. So it's about 11:24, and we're going to, or at least Central Time, and we're going to jump over to our Lunar Lab and one of our scientists there, Andrea Mosie. So I'm going to unshare my video so that Suzanne, who is in the Lunar Lab, can connect and show us Andrea Mosie there in our lunar facility. Now, as they're getting themselves set up, and I'm hoping that we'll see their camera pop up here, our lunar curation facility is a world-class facility that you're going to see right now with Andrea. And as Andrea gets started, she is going to share with us a little bit about her educational background, her journey to NASA, her career experience, and then the work that she does there. So, Andrea, take it away. Tell us about you and what you do.
Good morning. I am Andrea Mosie, and I am a native of Houston, Texas. I attended public schools in Houston. I attended Houston-Tillotson University, at that time Houston-Tillotson College, in Austin, Texas, majoring in chemistry and mathematics. Originally, I had planned on being a doctor, but over the years of my last year in college, I decided that I was going to switch my degree plans, and I had already taken all of my chemistry and math classes. I ended up having a double major in chemistry and math, and I graduated and applied for 3 different job opportunities, one of them which was at NASA, Johnson Space Center, another one at UTMB, Dow Chemical Company, and Nalco Chemical Company. I decided to take the job opportunity at NASA because at that time I realized that I did not have transportation to work. I had a sister and a brother-in-law working out in this area. That's actually the reason that I took this job, but I'm so happy that I did because I have actually loved everything that I do here at NASA, and I've been here for 42 years. This is the only career path that has made a lot of sense for me. So I'm totally happy with the decision that I made. I'm now standing in the Lunar Sample Laboratory, which is the laboratory where the Apollo astronauts collected samples from the moon. There were 6 missions that went to the moon from 1969 to 1972, bringing back 842 pounds of rock, 382 kilograms of rock, stones, and pebbles, and they are actually curated here at Johnson Space Center. And this
Andrea,
laboratory, yes.
Can I disrupt you for one moment? Some folks are having some problems seeing you. So for the folks on the line, we want you to see Andrea. We want you to see the lab that she's in. So if you notice to the right of your screen, so not the slide, but to the right under where it says participants, you might see, hopefully you were seeing Amy when she was chatting, and hopefully now you're seeing Andrea. So you should, under participants, you should be able to see Andrea there. Now, can anyone confirm in the chat room that you are able to see Andrea? We saw Amy, but we do not see Andrea. Okay, and can anyone confirm that they, not yet? So we're not seeing Andrea yet. Let me see what I can do about this.
I clicked on the very bottom icon where the windows were at the very bottom. I clicked that to drag that bar over.
Okay, so, and it might only be a small screen where you see Andrea, and that is, it should be on the right Now, in your little video screen where you saw, let me share my video again real quick so that we can see if that helps pop up any of the video there. And again, it should be a small screen. Unfortunately, we can't have the screen take over, but that screen, you can actually click on it to be able to see her better. So I see JCTMS can see her in the small screen. Okay, Lathrop can see her. Can anyone else confirm? Because this is really, Dave Safala, thank you, in the small screen. Having Andrea be in this laboratory, this is a place not everybody gets to go and not everybody gets to see. So I really wanted to make sure that you're able to see her in that small screen, and I'm seeing most of you are able to see her. You've heard her story. Hopefully the rest of you can see her as well. I'm going to leave my screen. Oh, they see me. Suzanne, I'm going to make you the presenter. Maybe this will help them to be able to see you in that screen there. So if you still can't see her, listen to her because she is excellent to hear and as well as see. So I apologize for interrupting you there, Andrea. I think they can see you now, so you are good to start again telling us about that lunar lab you're in.
Okay, thank you, thank you. The samples are housed here. We actually process them, which means that we take pictures of them, we weigh them, we send them out to scientists who actually do allocations that they have to request. Now, this particular laboratory is a working lab. Most people come and they view it, they think it's a museum, but this is actually a working lab. We give out at least 500 samples a year to scientists. We call them PIs, principal investigators, all around the world. The cabinet that I'm in front of right now is a display cabinet. All of the cabinets are nitrogen-filled cabinets, a very pure type nitrogen gas, and we are actually protecting the samples. In this cabinet, there are 5 different display rocks that we have set up for public viewing. 2 of them are basalt samples, and the other ones are breccia or impact melt samples. Also, you will see a tag in front of each sample with the 5-digit number on there. That number is the rock number. Every rock has a 5-digit number, and the first number or the first 2 numbers will actually tell you what mission the sample is. With Apollo 12, 14, and 15, those samples actually began with that number. With Apollo 16 and 17, they dropped the 1. So 16 sample will begin with 6, Apollo 17 will begin with the 7. Every sample that was brought back, the parent of that sample is (0), and every time you break it or you get a different split out that sample, you get (1), (2), (100), (2000), depending on how many times you actually split that particular sample. You will also see a small cube that says TNSBW, north, south, east, west, top, and bottom. The astronauts gave orientations to the samples. They took pictures on the moon so that we would know the orientation of those samples, and we keep that orientation in the lab. If any samples came back without orientation, we gave them a lab orientation, and then we still keep that orientation. Now, in this particular cabinet, and all these rocks were given, most of these in this cabinet were given names by the Apollo astronauts. And the one on the end that's Apollo 17 rock is actually called the Children of the World rock. This is a basalt sample, and you can look online and see the story of this. When Jack Schmitt picked up this Apollo sample, he actually said it was for the children of the world because at that particular time, there were children from countries all over the world watching the last, which was Apollo 17, space expedition that had landed on the moon. And he said this rock had big vesicles, small vesicles, dark spots, light spots, different things, and that was representative of the children all around the world. So this rock was gifted to countries all around the world in small displays. And so you may have a display in a museum in your city or country. The next rock is Apollo 16 melt rock. You'll see the glass coating on the top of that. This one doesn't have a particular story, but the white on there is anorthosite, and these are the same minerals that we actually have here on Earth, but the minerals on the moon, because there's no oxygen and no weathering process, or iron does not react with our oxygen to form rust, then these are called pristine samples. Our next sample, which is Apollo 15 basalt sample, a vuggy type basalt. You see the different size of the holes. This was called, and those were caused by gas bubbles. This is called Seatbelt Rock, picked up by Apollo 15 astronauts, and actually, when they were on the rover, and Apollo 15 was one of the missions that had a rover, they had gone out as far as they could without mission control telling them to come back, because you could not go further than you could walk back in case something happened to the rover. And one of the astronauts actually saw this particular sample, was interested in it, wanted to go and collect it, but mission control told them, no, it could not be done. It was time for them to get back. He got off the rover, went over, documented the sample, took pictures, bagged it, brought it back, while the other astronaut, which was, it was Jim Irving, who actually went after that, and Dave Scott picked up the rock and brought it back. And once they got back on the rover, he got his seatbelt hooked, and he told mission control we're on the way back. When they got back to NASA Johnson Space Center, and they documented and were counting off all the rocks that they knew that they were scheduled to pick up. They had this one extra rock and wanted to know where it came from, and that's when he said, aha, and he told the story of how he picked up this particular rock. So they actually named that Seatbelt Rock. The next large sample that you're looking at is called Big Muley. It was collected by the Apollo 16 astronauts, and it was given the name Big Muley after the geologist Bill Moberger, who actually taught the Apollo 16 astronauts geology. This rock was the largest rock brought back. It was actually about 20 pounds. You're looking at a salt surface of it right now. It actually had a big white crater on the top of it. You can only see a small part of it. And it also has zap pits on that. Zap pits were caused by meteorite impact on the surface of the moon, making those small impact craters, and they called micrometeorites, and they call those zap pits. And that's one feature you'll find on rocks from the moon that you will not find on any rocks from the Earth. And the next sample is actually Apollo 15 breccia sample. A breccia is a bunch of small rocks welded together into another, made into another rock by an impact, probably the surface of the moon being hit by a meteorite or another type of sample, which could be actually an asteroid. Now you're again looking into our Lunar Sample Lab. All our processing is done by mission, and we're going to look over at what we call data packs, because the history of every sample is kept in the data pack. The last sample that you looked at was Apollo 15, and it was 15459. We have curatorial orders which actually tell you what you're supposed to do for a rock. This is one of the old ones, and now, of course, you know, everything is digitized and computerized, so they are typed up and not handwritten. The first thing we do is we weigh the sample, because we have to keep accurate track of all the samples that go inside the cabinet and come out of the cabinet. And what I actually want you to see is the details that we take of the sample. The first thing we do is we take a picture of the sample from both sides of the rock, and this was done back in 1985. That every time a piece of rock is broken off, you actually give it a different sample number, and as we're going by, all of these pieces come at 246, 247, all of these are being given different numbers as the rock is breaking up, and that's what we wanted to happen. But in the end, you actually have to put the sample back together. It's like doing a puzzle. You get it? Because if a scientist asks for a piece of rock off of comet 253, and another scientist wants that same sample, but we've used it up, we could go back through our data packs and find that exact piece that they're looking for and give them a piece off of an adjacent piece of the sample so that when they do their analysis and studies, they will be working with the same rocks. This data pack has been scanned, so I'm trying to take my pages and rush through this. We also collect the fines and small chips and fragments. Everything is good sample. Everything has to be accounted for. You can't transfer 100 grams of sample into a cabinet, and once you finish processing, you have 60 or 70 grams. You need to know where all of the samples are. Walking through the lab, here's another Apollo 16 rock that and this is another breccia. And you'll just see the different samples. We work inside of these neoprene or rubber gloves. We work inside of these gloves. And why do you think we work in these nitrogen boxes?
So that's a question for you all to see if you can answer. Why do you think they have nitrogen in these cabinets where they work in the Lunar Lab? And so if you have any ideas on that, put that into the chat window. And we just have a few more minutes with Andrea, so we'll see what kind of answers we might get in the chat window. Now, Oak Forest is saying to not contaminate the rock because it's less reactive, comes from Ukiah School. Let's see what other answers might come in. Duxbury is saying so there'll be no oxygen contamination. And Anastasia says to provide a lunar environment to keep it cold. JCTMS thinks it's not the same air on the moon. And Caruthers Elementary is suggesting to keep them fresh because oxygen, I lost that, lots of great answers coming in, because oxygen makes things rust. That comes from Lathrop High School. Chester High School says no air to destroy it. So a lot of similar answers there. Andrea, why is there nitrogen in these cabinets?
And those are great answers. And because nitrogen is an inert gas, and we did not want the oxygen in the cabinet because, of course, yes, the samples would rust. So all of the correct answers were given. So we're working inside of these cabinets, and we're protecting the samples from us. We're not protecting us from the samples. When they first came back, they went into quarantine to make sure that they weren't bringing anything back to Earth that was going to be bacteria or anything that would be harmful to human beings. But now we are being absolutely sure that we're protecting the samples from us. You're looking at the Lunar Vault. That's the lunar sample vault. And all of the samples are kept in nitrogen environments in the vault. They're sealed in double Teflon bags and in hard containers. The only kind of containers that we use and only tools that we use in the cabinets are Teflon, aluminum, and stainless steel. Those are the only kinds of materials that we actually use in our cabinets. And so you're looking now inside of a Apollo 17 cabinet, and you can actually see some of the tools that we use, balances we use for operations. We have to weigh everything that we do, and you can actually see some other samples. We only open one sample at a time, one sample generic number at a time. So you see a lot of Apollo 17 samples in here, but they're actually bagged up.
Now, Andrea, we so appreciate, we wish we could stay in this lab with you for the whole day. I bet there are students out there that wish they could take their whole class into this lab with you, or at least be able to continue to look at this lab. But unfortunately, we have one other speaker that we want to be able to share with the group. And so, not that I want to cut you off, but for the folks out there, realize that, you know, we had Amy as our first speaker. Amy, you've been working here, what, 1 to 2 years? 1 year. Andrea's been working here for 42 years, still has, is that right, 42 years?
That's correct.
She doesn't look a day older than 17 or maybe 19 or 21.
I paid her to say that.
But we have one additional speaker that we want to share with you so that you can get even a broader sense of, we've done Earth, we've done the moon, and now we're going to take you to Mars here. So we're going to hold any additional questions for Andrea until after our next speaker. Andrea, will you stay in the lab if we have additional questions for you?
Yes.
Okay. Then stand by, Suzanne. I'm going to grab the ball back. You can unshare your camera, and boy, do I wish we had more time. But we're going to move on. And again, thank you, Andrea, for the time being. Stand by, and we're going to move on, switching gears from, again, Earth to Moon. And now we're going to go to Mars, and we'll try to answer as many questions after the top of the hour as possible. But our last speaker for today, Joanna Clark, she's going to talk to us about her journey to Mars. So, Joanna, take us to Mars with you.
Hi, everyone. I'd like to thank you again for tuning into this webinar about our journeys to NASA. My name is Joanna, and I'm currently a scientist with the Mars group at NASA Johnson Space Center. I'm going to tell you a little bit about my job later, but for now I want to tell you a little bit about my background and how I got my job at NASA. So I grew up in upstate New York in a town called Glenville, which is right over here, and I went to Mosquito High School, which had a total of about 1,000 students. During high school, I was very interested in sports. I played varsity and travel softball as well as the indoor track all 4 years of high school. And this is just an embarrassing picture of me at a track meet in high school. I also really enjoyed science classes, especially earth science and chemistry. I had a really awesome earth science teacher when I was a freshman in high school, and he was really the person that got me interested in earth science careers. When I was a junior in high school, I started looking at colleges that had geology departments. I applied to several state universities in New York schools, also called SUNY, because they cost a lot less than private schools. And one website that I found really helpful when planning for college is called collegeboard.com. And this is just going to show you how to study for the SAT, how to pick a college, how to plan for college, and a lot more. I ended up getting into SUNY Geneseo, which is a top state school in New York, and this is just a picture of me before my high school graduation. The first year of college was actually pretty difficult. It was really hard to be so far away from family and friends, and I was taking a lot of classes that were a lot higher level than they were in high school. But there were a lot of resources in college that I took advantage of, like professor office hours and study groups. In college, I ended up majoring in geology and minoring in biology, and I also took a lot of upper-level chemistry classes, which really helped me. And these are just a couple pictures of me at my graduation from Geneseo. Right after graduating from Geneseo, I went to University of Alabama for my master's degree in geology. My master's degree was focused on paleoclimatology, which is the study of the Earth's climate change through fossils. Although I studied paleoclimatology, I learned a lot of chemistry along the way. After graduating from Alabama, I moved to Houston, Texas to look for a job. I probably applied to about 50 jobs before I stumbled upon an open position at NASA Johnson Space Center. The interview went really well, and I was offered a job as a research scientist with the Mars team here. So now I'd like to tell you a little bit about my work at NASA Johnson Space Center. I'm a research geoscientist with the Mars team. My job is to look at science data coming down from the Curiosity rover on Mars, which is shown here, and I try to explain what it means by running experiments in the lab. I'm also becoming more involved in Curiosity rover operations. Soon I'm going to be sending commands to the rover, which will tell one of its science instruments how to operate. Before I get what I do specifically, I want to share a few basic facts about Mars for those of you who are less familiar with it. Mars is sometimes called the red planet because of this reddish hue of its surface materials, and it's about half the size of the Earth. Its atmosphere is made of mostly carbon dioxide, so we as humans wouldn't be able to breathe on Mars. There's also much lower gravity on Mars compared to the Earth. So for example, if you weighed 100 pounds on Earth, you would only weigh 38 pounds on Mars. In order to investigate our neighboring planet, we've sent several orbiters, rovers, and landers to study Mars up close. The goal of all of these missions has been to find evidence of liquid water, explore habitability, seek signs of life, and also prepare for future human exploration. So the current Mars rover that we're working with is called Curiosity, or Mars Science Lab, and we're circling it right now. Curiosity was launched from Cape Canaveral in Florida on November 26, 2011 in an Atlas V rocket, which is shown right here, taking off. So Curiosity then landed on Mars in August 2012, about a year later, in Gale Crater, which is about the size of Connecticut and Rhode Island combined. So this is an image of what Gale Crater looks like from orbit, and the star is where we landed Curiosity, and the green circle-ish thing is the landing ellipse, where we kind of wanted to land Curiosity. So the spacecraft carrying the rover landed in 4 main steps. First, small rockets control the spacecraft's descent towards the Martian surface. Then, a large parachute controlled the spacecraft's descent towards the Martian surface again. And this is just an image that's taken by an orbiter. So the way to understand this image is on the left, that's what you see from the orbiter, and the right is the same exact image, but it's blown up. So it's the same exact thing, it's just a little closer. And the top part is that parachute, and then the bottom part is the spacecraft, which actually carries the rover. So after this, some more rockets came out, and they slowed the spacecraft even more. Finally, something termed a sky crane lowered the rover, wheels down towards Mars. And this is a picture of what the landing may have looked like from Mars, not an actual image. Curiosity has a few main goals. First, we want to assess whether it's possible for life to have ever existed on Mars in the past or present. We also wanted to study the types of rocks and the chemical makeup of the rocks on Mars and kind of see what it can tell us about Mars. We also wanted to see if there was any evidence of past or present liquid water, as well as what the weather and the climate is like. Finally, we wanted to see what are the different hazards on Mars, such as high radiation. And this is going to tell us what we need to keep in mind for future human missions to Mars. Curiosity is essentially a robotic field geologist. It's a large mobile science laboratory that has a long life and the ability to travel many miles over rough terrain, such as large, sharp rocks. It has 11 science instruments on board, and these test the mineralogy and the chemistry of Mars. It also has the ability to take images with several different cameras, and it has sensors to monitor water, radiation, and weather. So I want to pause really quick and ask a question just for fun. Can anyone guess how fast the Curiosity rover can travel in centimeters per second? And just remember, there's about 2.5 centimeters in 1 inch, which is about the size of your thumb. So if you think of an answer, just type it into the chat window, and I'll tell you the answer in a couple minutes.
All right, so how fast in centimeters per second, just very quickly in the chat window, how fast or slow do you think this rover can travel? And we'll see what kind of answers we're getting in the chat window. Now that's a tough, think about your car, you know, how fast your car drives, certainly in not centimeters per second, but we're getting some answers in, and I'm seeing 10 centimeters per second, 6 centimeters per second. Lathrop is saying 50 centimeters per second. Vintage Magnet says 25 centimeters per second. Oak Forest says 15 centimeters per second. We've got a range of 5 centimeters per second from Vintage, 7 centimeters per second from Chester High School. Anasazi, 25. Vintage Magnet's thinking, well, maybe it's 115. I mean, 115 centimeters per second. Duxbury says 30 centimeters per second. So we're getting a range from about 6 or 7 up to 10. Ukiah School says less than 5. This is interesting to think about. Joanna, how fast or slow does the rover travel?
So a lot of you are actually really close. The rover actually only travels about 4 centimeters per second, and this is actually slower than most land turtles.
Very interesting.
So as I mentioned before, Curiosity has 11 science instruments on board which measure different characteristics of the Martian surface and atmosphere. The instrument that I primarily work with is called SAM, or Sample Analysis on Mars, which she's circling right now. And you can't really see it in this picture because it's actually inside of the rover, but that would be the general location. SAM is basically an oven that heats a solid sample from the Martian surface. It heats a sample all the way to about 900 degrees Celsius or 1600 degrees Fahrenheit. And as it's heating the sample up, the sample produces gases. These gases are then delivered to something called a mass spectrometer, which tells us what's in the gas. For example, does it contain water vapor, carbon dioxide, or oxygen? Based on what's in the gas, we as scientists can get a better idea of what types of rocks and minerals are on Mars. A good analogy to this is baking cookies in an oven in your own kitchen. So as the oven heats up the cookie dough, it starts to produce different smells. Your nose acts kind of like a mass spectrometer by telling you, hey, these cookies are smelling pretty good and they're probably done. As the oven keeps heating those cookies though, and they become burnt, your nose identifies a very different smell that says, hey, these cookies are smelling pretty bad and they're probably burnt. The SAM instrument is very similar to an oven because it tells you what material it is based on the gases that it's being produced when it's heated. So in a way, your nose is kind of like a mass spectrometer. So this is a picture of the lab that I work in a lot, and it has a lot of different instruments in it. 3 of these instruments contain mass spectrometers and are meant to be very similar to the SAM instrument that I just spoke about, which is on the Curiosity rover. And one of my jobs is to conduct experiments in the lab to help explain the data that we're getting down from Mars. So basically, through experiments, I can help say what chemicals and minerals are present on Mars. So finally, I wanted to give you a quick example of one of the experiments I did. So this graph is an example of what data from a mass spectrometer might look like. The x-axis, or the bottom axis, shows temperature which increases to the right. The y-axis, or left axis, shows how much of a certain gas that we have, and it increases upward. This particular graph shows how much of a certain gas we have, which is called oxygen. So, and it's from the sample rock nest, which is shown in this picture right here, and also shown in the red curve. So as you can see, the peak amount of oxygen that's released is around 375 degrees Celsius. And I ran multiple laboratory experiments using different chemicals and minerals that may be present on Mars. And I found that the chemical magnesium chlorate, which is shown in this blue line, produces oxygen at about the same temperature as rock nest. So this tells us that the chemical magnesium chlorate may be present in rock nest sample on Mars. And this is just one quick example of what I may do in the laboratory on a daily basis. So lastly, I just wanted to say that we need students like you all watching to be scientists and engineers of the future so that we can explore Mars and possibly even send humans there. Overall, I really enjoy my job as a scientist at NASA Johnson Space Center. I never thought that I would have this job when I was your age, but it's completely possible with hard work. So now if anyone has any questions, if we have time,
Absolutely.
Into the chat box and I can try to answer them.
And, you know, just to say, this very simplistic plot that Joanna showed, is it kind of like how every person has their own individual fingerprint, every mineral and element has their own fingerprint as well, and you just look at it in terms of these spikes and peaks and things like that?
Mm-hmm.
So that is, you know, a simplistic view of that, but boy, can it get complicated. Now, it is 11:57, and for many of you, as we get close to the top of the hour, you may have to depart and take off and go on to your next class period. Before we go into questions for Joanna, as well as back to Amy and Andrea, I sort of want to officially say, thank you so much for joining us today. We obviously needed more time. This is the first time we've ever had 3 speakers in one, 3 fantastic scientists that all wanted to be able to share their journey to NASA as well as their science with you. But as time is so short, for those that do have to depart, we thank you so much for joining us, and we will archive this recording so that you can watch this later. For those that can stay on, we're going to stay on 15, maybe 20 minutes to answer questions that you may have as long as our scientists can stay on the line with you. So since Joanna was our last speaker, I definitely want to take a couple of questions for Joanna first. And again, if you have to depart, again, thanks for joining us. Have a great holiday season, and we look forward to doing this again soon. We're going to have to do that. So for questions for Joanna, one of the questions, Joanna, I saw come in was, what's the size of the rover and how much does it weigh? Do you know anything on that, Joanna?
So the rover is actually about the size of a car, and it weighs about 2,000 pounds, which I believe is 1 ton.
So that's a mighty heavy rover, and if you think of it, we've had a Mars exploration rover. Those are about the size of a golf cart. This is, I think I've heard, about the size of like a small, like a Mini Cooper. Is that right?
Yeah, that's right.
Yeah, so you could drive this kind of thing, but so it's one of the largest rovers we've ever sent to Mars. Awesome. Now, one of the schools is asking, Anasazi Elementary is asking, has the rover ever stopped working? And Lathrop is also asking, sort of similar to that, has the rover ever broken down, and what do you do about that?
So in the past, so it's been there since 2012, and there have been issues with the rover. I don't know exactly which ones I can mention publicly, but there's always a way to fix it, and obviously we can't send humans there as a mechanic to fix it, so all of the fixing that we do is through software. So we have really great computer scientists that work at JPL and NASA that will send commands to the rover to test whatever instrument or whatever is actually malfunctioning, and then send commands that will fix it.
So it's kind of
like, there's always backups of a lot of the things on the rover, so we can go switch the backup if one thing malfunctions.
Excellent. And it is an issue that is hard to be able to deal with, but even things such as the tires and the wheels on the rover. Have we had any issues with the tires and the wheels that you can talk about?
Yeah, I wasn't sure which things I could talk about, but that happened a long time ago. So the wheels are actually made up of aluminum, and when they sent the rover to Mars, they had tested it on Earth, and the wheels were fine. But what they didn't realize was that the rocks on Mars are actually very sharp, and when you drive over it, they stay in place. They don't fall down like a lot of rocks would on Earth. So they're pretty much just daggers just sticking out of the ground. So when the wheels went over them, it kind of tore the wheels up. So that kind of messed the wheels up a little bit, but they're still usable, and the way that we work around it is we have cameras on the rover, and we direct our the path to go around any rocks that look sharp. So we just try to avoid all obstacles so we don't further damage the wheels.
Awesome. And that's less of a software problem and more of a hardware problem.
Hardware issue, but we work around that.
Yes. And it's creative engineering. Oftentimes these problem-solving things that they do is sort of, in a sense, looked at as creative engineering because you have to design solutions for things that you've never had to deal with before.
So it's one thing they didn't expect.
Exactly. So who would think you need a spare tire on Mars with a Mars Curiosity rover? Now, I want to go back to, in case there's some questions for Andrea while she's perhaps still in the lab, I know there were some questions that came out. I saw Dave Zavala had a question for Andrea about the rocks and the numbers. So, Suzanne, I don't know, I've made you the presenter again so that you can share your camera and unmute your phone, Suzanne, to see if you could have Andrea explain a little bit about, why do we have these numbers for these rocks, and is there any rhyme or reason to how these numbers came about? So we can see you. Hopefully the rest of the folks out there can see you. Here's Andrea.
Okay, each mission had a different, basically, numbering system. The Apollo 15 rock that I was telling you about begins with the 15, which is meaning Apollo 15. The next number, which was the third number, 4. There were different stations on the moon, and they picked up rocks at station 1, 2, 3, 4, 5, 6. And so that was picked up at station number 4. Possibly that could have been the 59th rock that they picked up. But in the data packs and in the voice transcripts and the other data that the astronauts collected that we have in a vault, we have a data vault that's full of data packs like I showed you, and all of the information is stored in there, and you would know exactly the numbering system. There is a reason for the numbering system because they want to know exactly where every rock was picked up, and it's important that they knew where they were picked up so that once we're processing the samples, we break them, we allocate them. There are scientists that may have done studies on them 30 years ago that are still have students who are coming behind doing studies, and technology instrumentation is so much better now. They're either going to fine-tune what the analyses were, or they may totally counteract it. So every year we have a lunar science conference here in Houston, and scientists from all over the world come in and they present their abstracts and studies, and it's really interesting with their findings about the moon.
That's totally awesome. And, those numbering systems, even with the astronaut imagery and some of the numbering systems, is sort of hard to grasp. What does this all mean, and how did these things get their associated numbers? But it almost becomes the name of that sample or that image so that people can identify and request from a particular sample or request an image. Now, Andrea, another question we had gotten from Vintage Magnet was, how many other people work with you in this department? And can you kind of explain your department and how many people sort of work with you?
Actually, in this particular lab, which is the Lunar Sample Lab, with Apollo samples only, we have 4 other lunar sample processors, and 2 of those 4 actually cross over into another laboratory, which is the meteorite laboratory, because in our area we have curation of lunar samples, meteorite samples, stardust, Hayabusa. There are actually 7 collections. So we all work in one specific lab, but we have the ability to cross over and work into the other labs to help those sample processors with their studies as well.
So there is more than just one lab, and is there a facility like this anywhere else in the world?
This is the only facility where lunar samples are housed, processed, and actually the scientists come here and pick out their samples after going through the approval process through a group, a committee called CAPTIM, which is Curation and Analysis Planning Team for Extraterrestrial Materials. They actually have to put in a request. They submit their request. This committee will approve or deny depending on what they're actually asking for before we actually send samples to them for analysis.
That sounds pretty tough, like you've got to do a whole lot in order to be able to get those samples allocated to the respective scientists. So they've got to really make sure they're doing some good research.
Yes, it's not an easy process. But one thing I want to show you, which Suzanne is showing, every cabinet is a different mission. This is Apollo 17 cabinet, and only Apollo 17s are processed. Every one of these cabinets is for a specific or different mission.
So no mixing and matching?
No mixing and matching. The only cabinet that has mixed samples was the display cabinet that we showed you at first, but we don't process samples in there, so there's no way that a piece of one could be mixed up with a piece of a different rock.
Awesome. Now, here's a question for you, and I'll ask the other folks here, our other scientists. Some of the students were asking, how much training do you need and in what subject areas? And this came from Chester High School. So if someone wanted to be a scientist like you working with lunar rocks, what do they need to do to prepare themselves for this type of work?
Actually, math is really important because of our number system and because we have to balance everything. You have to be pretty good in math. I mean, but you have calculators and everything, so we could keep track of all the samples, but attention to details. You have to pay attention to tiny details because we need to know if you're looking at a sample, if you see a particular mineral, if they're requesting a certain thing, you have to be able to select or pick out the exact sample that scientist or that PI is actually looking for. I think you just have to have a love of science. I had no idea that I was going to even be interested in working with rocks. It's just something that happened once I started working here. You had to have a science-related degree. So I had the chemistry background, I had the math background because I've always loved sciences. And once I got here, I started working in the field of geology. So I got my master's degree in physical science and geology. Now everybody that works in this particular laboratory has a master's degree in geology or physical science.
So math and science is really important.
Yes, yes.
And a passion and working hard, you would also say, is a part of that as well?
Yes, I just think you have to love what you do. And once you start working here, you really will love it. And if you just see right now, we have another geologist who is coming. You asked who else work in the lab. This is one of our other geologist who has just come in to work on some Apollo 16 samples, Sharif. And so, yeah, you see Sharif on there now.
Hey, Sharif, and thank you, Andrea, for answering those questions. And we might come back to you, but I want to ask the same question to Amy here. And I'm just going to grab this to make sure we can see Amy. And Suzanne, we might come right back to you. Amy, this actually came in during your question or during your little part. How many photos are taken in a day, if you can answer that on average, and what recommendations do you have for students and what they should maybe study?
Okay, so astronauts will take images of not only of Earth, but when they do take images of Earth, sometimes it's not of of the targets that we send. A lot of times, this is something that astronauts will do on their free time, and it's fun to do. So an astronaut, within their missions, I think Terry, who was a recent astronaut with Samantha, took about over 300,000 photos. So, and I'm approximating on that. So,
so it can be 1,000 images a day or
right.
A handful of images a day.
And sometimes we won't, sometimes we won't get any images of our targets for a day. And sometimes, we'll receive 5 or 10. So during IDC times, during the International Disaster Charter, we'll definitely see an increase in image acquisition. So, something that maybe 5 images for a target or 1 image for a target could increase to 20 or, even 30 or 40 images for a target.
And our database as a whole, that eol.jse.nasa.gov, has millions of images that you can actually look at and see. So over time, we've been taking images since the 60s.
Yes.
So that's a lot of images that have been taken. And how many people in your group that you work? What's the name of your group, and how many people work within that?
Okay, so we're the Earth Science Remote Sensing Unit here within ARIES. And the amount of people that work within our group, somebody recently just retired, but it's probably about 5 or 6, and you know, we all have similar duties in different disciplines as well. So yeah, I would think about 6. I'd have to count this me and you. Yeah, so it's about 5 or 6.
So that's a smaller group. I will say this, if you look at the bottom of the screen, our division, our Astromaterials Research and Exploration Science Division as a whole, we have 180 to 200 scientists. That's both contractors and civil servants that work as a part of our division. We study Earth. We have our curation facilities with the lunar samples, meteorites, and other astromaterial samples. We have a research group. We have orbital debris researchers. We have image science and analysis folks. So what you've heard today is a small little piece of the couple of hundred of scientists that we have that work here as part of this division. So it's really interesting, and the pathways are all slightly different. Now, before you talk about any like needs for college and things, I just want to jump to slide in here, or we can even move the camera. So Joanna, as part of the Mars group, how many people in this group for the Mars research group, both here at Aries and JSC as well as holistically?
Oh, wow. Okay, so here, again, I would have to count, but it would be probably around 10.
Okay.
Because here, MSL, which is the Mars Science Laboratory team, which I'm a member of, is probably hundreds of people from all around the world, actually. I think most of them are probably in our country. And then there's a lot of participating scientists that work at universities, and that just kind of adds to the group. So there's a lot of people that even research Mars, but they aren't directly involved with the Curiosity rover, and a lot of times they'll work at universities. But the MSL team, which is the rover team, is probably a couple hundred, and here there's probably around 10, I would think.
Okay, so again, these are very specialized groups that are part of a bigger entity. So, you know, when Joanna said she put in applications for like over 50 jobs and finally got this position, things are very competitive. So those grades, that hard work that you guys do in school, that you put into everything that you do is so important. And Joanna, we had a question that came in from Vintage Magnet, and I see that they're still on the line. And they're wondering how many rovers are still functional on Mars?
So I believe, Mars Science Laboratory, Curiosity, and Opportunity is still active, but it's not the main one that we are interested in right now. But there have been plenty of other rovers that have been on Mars since, I forgot when,
Probably our first lander was in the 70s, 76 with the Viking landers.
Yeah.
And, you know, the Opportunity rover that Joanna mentioned, it has been at Mars for over 15 years. Gosh, we launched in 2005, I think. The Mars exploration rovers, I'll give you a sense, 90 days was their sort of, here's how long we think they'll last on the surface of Mars for the Mars exploration rovers. And it's been over 10 years, and the rovers are still going. Yeah. Mars Science Laboratory, what was its mission success? How much time?
I think we're in the second extended mission right now. So the lifetime of the rover really depends on the different instruments on it. So one instrument may stop functioning, but the other ones may still be working. So for example, when I work on the sample analysis on Mars, which I mentioned was that mass spectrometer, which analyzes gases. So that could last, we don't really know. It could last another year, it could last another few years. But once that one dies, then there may be several other instruments that are still working. We hope to have it around for several more years.
There's certainly a lot to explore.
Yeah, there's a lot to explore on Mars because it's a planet we've never been to and everything is new. And even when this one is no longer functioning, we'll probably have another rover on Mars at that point.
When's the next rover?
Mars 2020 is in the works, and that's going to launch in 2020. And there's another one, I forgot the name of it, but it's mainly a geophysical themed rover.
The InSight mission,
yeah.
Which will be a lander mission that will not rove, but it will look for any kind of seismic activity on Mars. And that InSight, I think, is scheduled to launch, if I'm not mistaken, in 2018.
That sounds right.
Yeah, so lots of action at Mars. If we're preparing for humans to go to Mars, we certainly have to do the groundwork with current missions at Mars, as well as NEMO-like missions, the NASA Extreme Environment missions that Amy talked about. And also we have to be able to learn from things we have done on the surface of the moon, like with the work that Andrea has showed us the results of in those samples. Now, I know we have probably a million questions that I missed in the chat window, and I see the Ukiah School is still on the line, Oak Forest, Lynn Haven, and a few other schools, Leon Springs, Lathrop, Zavala, Chester High School. Can you put in any more questions you have, because I might have missed them all the way up, for any of our speakers, because I know there were so many great questions, and so if there's any other questions that you want to try to get answered, now is your time. Thank you, Lynn Haven and Miss Ackerland, and thank you also for the De Zavala School. I realize your students sometimes they have things they've got to do, whether it's lunch or the next class period. But are there any other questions? I know with a couple of high schools we have on there, Lathrop from Alaska, as well as Chester High School in Chester, Pennsylvania. Any additional questions we can try to answer for you?
Paige, there was one question that I got. This is Andrea.
Oh, yes, Andrea.
I was asked how many samples did we have. We collected, or the Apollo astronauts brought back 842 pounds of sample, which was almost 2,200 different rocks, pebbles, or fragments, and now those samples have been broken up into over 120+ thousand samples that we actually have in the lab on inventory for research and that we sent out to the PIs all around the world.
Thank you for identifying that question. And Suzanne, if you'd like to share the camera there at all, you said 842 pounds that are broken into how many samples?
Actually, probably closer to 150,000, but I'll say 120+ thousand. Every sample gets a number, and every time we split a rock, it gets a different generic number. So all of those samples are on inventory in our database, and we have them either here at our facility or they're out to principal investigators all around the world who are actively doing research on them.
So you all keep track of 150+ thousand samples, where they are, how much they weigh, what's happening to them, where they're going, and all of that stuff?
Absolutely.
And there's how many of you in your group?
Actually, in our Lunar Lab, there are 4, but we do have a database. We have a database group, and we enter the data into the database, and it's a team effort, and it's a great team. So we all get along and work very well together.
And, you know, that makes me think of another question I saw come in related to the Apollo samples, and that was how are these samples similar or different from rocks we actually have here on Earth?
We have the same minerals. Rocks here on Earth have the same minerals. We have ilmenite, plagioclase, olivine, same minerals, but because of the atmosphere of the moon and the atmosphere here that we have, or the lack of atmosphere on the moon and the atmosphere we have here on the Earth, oxygen reacts with those minerals, and so someone gave that in their answer when I asked about the cabinets. Our samples will rust. The iron phase here in our samples will rust in our atmosphere, whereas on the moon they sit in a perfectly pristine condition. That's why the samples we have here in the nitrogen environment, we call those pristine samples, and then the samples that have gone out to scientists for studies, never come back to this particular lab. They never come back into the nitrogen environment. They go into regular cabinets, and they're kept in air, and they're processed in air.
I see. Now, we just saw Cherise stick her hands into those gloves, and it didn't seem very easy. Is it challenging? Why are they sticking out like that? Can you share any of that with the students since you just saw this?
It is challenging, and I'm just going to get Cherise right here so that she could say something to you. It takes practice. So you see Cherise working in the glove. She said it takes practice, and that's absolutely correct. When a processor is hired, they don't come and just absolutely know what to do immediately. It's a training process. We have to break the samples, show them all the tools and containers, everything that you see her working with has been cleaned, and there's a process. We have a procedure for everything. There's a procedure probably for the procedures. But so everything that we do here inside of the nitrogen glove boxes or cabinets is very strict, and we have to adhere to details. So that's one of the things that I said one person would have to be is a person that adheres to details.
Yes, attention to details.
And patience. A lot of patience.
And that was Cherise saying that you need a lot of patience.
Yes.
And, you know, it's so great for those schools that are still out on the line to have been able to, you know, you're watching the lab in action, and with Amy and Joanna here, you're talking that people that do very specialized work in very specialized environments and with very amazing types of exploration that is going on all across NASA centers, especially here at the NASA Johnson Space Center. So I know that there's still a few groups that are on the line, and if anyone has any additional questions they want to ask, now's your time. There's a few groups left. If you want to ask anything, otherwise we'll probably bring this to a close very shortly. But does anyone else out there have any additional questions they'd like to ask before we do bring this to a close? And I'll give it a couple of seconds to see if anything comes in. And if you're typing while I'm saying my closing remarks, and we'll see what question comes in. But, you know, we had groups from literally all across the nation here today, and I know today Safala is still on the line, perhaps without students, but Lathrop High School from Alaska, Leon Springs from good old here, I think that's our San Antonio group, and Lynn Haven in Florida. Those groups that are still on the line, we so appreciate you taking the time out of your day to join us here. And I also want to give a special thanks to the crew here that really made this happen, not just our guest speakers of Amy, Jagge, Andrea, Mosie, and Joanna Clark, but also Suzanne Foxworth, who is there with the camera in the Lunar Laboratory, enabling us to be able to connect with Andrea, as well as Cherise, who's a special guest that popped into our presence here. And on behalf of all of us here at the Astromaterials Research and Exploration Science Division, we so thank you for having an interest and for joining us today, and we certainly hope to be able to connect with you sometime in the future. In terms of websites, I'm going to put in our ARES website so that, and it's actually there at the bottom of the screen. Our ARES website will actually give you a whole lot of, I can't type and talk at the same time, a whole lot of resources, and if you look under outreach in the right-hand side of that page, it will give you some teacher resources, some activities that you might be interested in sharing with your students. So let us know if you have questions on that, especially to you teachers out there. But again, on behalf of all of us here, not just our 3 speakers and Suzanne and I who helped to facilitate this session, we want to thank you for joining us today. We look forward to connecting with you sometime again in the future, thanks for your participation. So I guess in the meantime, that's it. Signing off from the Johnson Space Center. Have a happy holiday season. We hope to do one of these again, potentially in January or February. It all depends on people's schedules and time permitting. But we hope to do one again early next year. So thanks again. Happy holidays, everyone. And thanks again for joining us.
Bye. Happy holidays to everyone.
Thanks, Andrea. Thanks, everyone. Thanks, Amy and Andrea and Joanna. Bye-bye.